do a smidgen of review before we get started again. All right, so last time we also defined enthalpy, okay? The definition being the heat transferred during an isobaric process, right? We invented enthalpy so that we could have a state function and we could relate to heat flow, okay? And last time we went through these steps to get from the first law, plugging in our PV isobaric work to get to our enthalpy equation. Okay. Most biological processes occur at atmospheric pressure and with negligible changes in volume. Okay. Meaning that our equation for enthalpy, we can write it out in a differential form as dH would be equal to du plus pdv plus vdp, but both of those last two terms are going to drop out. Okay. Making enthalpy very useful for estimating changes in internal energy for us. Okay. And this is very valid because also we have it set equal to our isobaric heat flow. So we can, by looking at changes in heat, understand a change in internal energy, which is what we really care about, but is very difficult for us to measure directly experimentally. Changes in heat flow are much easier. What technique do we have to measure heat changes? What was that? Calorimeters. What was the type of calorimetry we did last time? Isothermal titration calorimetry, or ITC, is what we talked about last time, okay? We're going to talk about a different one this time, okay? Differential scanning calorimetry, or DSC. What property do we need in order to study this stuff? What was a property that we defined right after enthalpy last time? The last thing we did, heat capacity, okay? So just a reminder, the definition of heat capacity, the amount of heat required to increase the temperature of a certain amount of substance by 1 degree Kelvin, okay? It's an extensive property with units of joules per Kelvin. Again, this makes sense, it's heat flow per degree temperature change, okay? Specific heat is heat capacity for a given unit mass, such as moles or grams, okay? This would then become intensive. And so again, we need heat capacity because what we're able to do is we're able to put heat into something or watch heat flow out of something, and we can also look at relative changes in temperature, and so we can record these two things and get some information about protein unfolding, drug binding, whatever it is we care about. We had two different heat capacities that we talked about last time. The isometric heat capacity and the isobaric heat capacity. Okay, so for constant volume, we'll use a subscript lowercase v, and for constant pressure, we'll use the p subscript. Okay. I'm not going to go through these proofs again. Okay, we did them on the notes, and then they're here in the slide for you as well. For an ideal gas, okay, not for everything, just for an ideal gas, isometric heat capacity or constant volume heat capacity is a constant. It's 3/2 times the number of moles you have times gas constant. This was also for a monoatomic ideal gas. So again, our most simplified sort of situation or assumption. We also went through the steps to get our constant pressure heat capacity. Constant pressure heat capacity was higher, 5/2 NR. This made sense to us. At constant pressure, some of the energy is dissipated as work done by the system on the surroundings or expansion work, okay? So in this case, constant volume, we're not doing any pressure volume work. All of the heat that goes in goes to raising the temperature, okay? So our heat capacity is sort of how much heat it takes to get a single increase in temp. It doesn't take as much because all it's doing is raising temp, whereas in the case where we can have movement and have expansion, some of the heat that goes in goes to raising temp, and some of it goes into moving the piston, okay? So it takes more to get 1 degree. It takes more heat flow in to get 1 degree temperature change. And CP is more relevant for our biological processes, but moreover, we're going to have potential energy consideration. So it's increasingly